So good afternoon, everyone, and welcome to our IPARCOS seminars. Today, it's my pleasure to introduce Dr. Amelia Fraser-McKelvie. After completing her PhD at Monash University in Melbourne, Australia, Amelia took up a postdoctoral position at the University of Nottingham, UK, followed by a postdoc at the International Centre for Radio Astronomy Research at the University of Western Australia, despite not being a radio astronomer. For the past 1 year and a half, she has been working as a fellow at the European Southern Observatory in Garching, where her research has primarily focused on exploiting intergraph spectroscopy data, including the SAMI manga survey. More recently, her work has involved analysis of MUSE data from both large survey and targeted smaller, highly resolved samples. Amelia is the deputy lead of the GECKOS survey, which stands for Generalizing Edge-on Galaxy and Their Chemical Bimodalities, Kinematics and Outflows Out to Solar Environments with P.I. van der Sande. This is an ESO large program on the VLT MUSE. GECKOS is currently observing 35 edge on this galaxy with Milky Way-like masses to assess the importance of internal and external processes in shaping the evolution of these galaxies. She is the lead developer on the NGIS software package and one-stop shop for stellar and gas property of nearby galaxies. Additionally, Amelia is heavily involved in the MOVE project, another ESO VLT MUSE large program, which stands for MUSE and ALMA, Unveiling the Virgo Environments. MOVE will observe 40 galaxies at various stages of infall into the Virgo cluster, aiming to understand the role of environment in shaping both the stellar population and the interstellar medium within galaxies. Her research interests center on nearby galaxies and understanding the role of internal structure play in driving galaxy evolution over cosmic time. Today, Amelia will present her talk, Star Power, Insight into Galaxy Structure and Evolution from Resolved Stellar Kinematics. So thank you very much, Amelia. The floor is yours.
Thank you, Enrico. What a lovely introduction. So let me just share my screen. Okay. So thank you all so much for the invitation. I'm very happy to be speaking to you all and sharing a little bit of my recent research, but also just insight into galaxies in general. So I like to start all of my talks with this slide, whether they're public talks or research talks, all the same. These are galaxies, right? In the local universe, so redshift 0, these are optical images, but this is just a small sample of the immense diversity of structure or morphology that we see in the local universe. Beautiful, beautiful galaxies. And you can see from this diversity, we see all sorts of structures. You know, we see shells, we see bars, one of my favorite structures, this little ring in the center that looks like the Eye of Sauron. You've got star-forming regions, you know, and you've got edge-on galaxies, you've got small galaxies, you've got big galaxies, different colors, different structures. And so what this is telling us is that, you know, these all started off as blobs of gas, dark matter, and angular momentum several giga-years ago. But these days, they look very different. So there must be an array of galaxy evolutionary mechanisms that have acted on these galaxies in varying ways. And so the name of the game is to understand what these mechanisms are, right? That's galaxy evolution science. Now, the eagle-eyed amongst you will see that there is an interloper in this collage of images of galaxies, and that's that one down there. That's not really a galaxy, is it? Well, it's an artist representation of our own Milky Way. And so on top of understanding how all other galaxies form and evolve, it's important to also be comparing to our own galaxy and our own observations of the Milky Way to put it in context and to understand how it formed in relation to its siblings, right? So how do you make a galaxy evolve? Well, in my mind, there's kind of two categories of processes. So that is your internal factors and your external factors, meaning things that happen inside the galaxy and things that happen to the galaxy or acted on from external forces. So in terms of internal factors, we have things like outflows, galactic fountains, AGN, things like this. You'll have to excuse my simplified keynote renditions of very complicated physical processes, but I did what I could. So you see something inside the galaxy is exploding and ejecting gas out into the halo. Some of it escapes, some of it rains back down onto the disk. Okay. Other internal factors include what we call secular evolution. Secular can just mean slow, but in this case, I mean in the terms of the growth of internal structure. So I mean bulges and bars and things like that. And then the third process I wanted to highlight of internal factors is radial migration. So this is a net movement of stars over time from their birth radius. So as an example, the sun is at about 8 kiloparsec from the center of our galaxy. We think it was born at about 6 kiloparsec. So it's moved about 2 kiloparsec in 4.5 gigayear. So that's fairly significant. So to be understanding the evolution of galaxies, we need to understand this net motion of stars, what's triggering it and to what extent it matters, right? So moving to our external factors, we have mergers, right? You fling two galaxies together. Mergers can destroy the disk of a galaxy. They come in at the right angle, if it's a large enough merger. And we think they can also build bulges, and that's a term we're going to come back to as well. Other external factors, large-scale structure. So that's filaments of gas supplying cold gas onto the galaxy disk. And then finally, I've just sort of used an umbrella term of environment. And so by that, I mean not both your large-scale structure, but also your nearest neighbors as well are affecting galaxy evolution. So the idea is that all of these mechanisms act together and different, different importance on every galaxy. Okay, but the problem is that we need to disentangle these various processes from one another, and they're all acting on different scales, and they are affecting different phases of the galaxy. So that's why I say understanding galaxy evolution is a multi-scale and multi-phase challenge. That's one of the reasons we haven't solved it yet, but one of the reasons that I'm still in a job. So the one thing that most of these processes had in common, except for mergers, is that most of the time these processes don't destroy a galaxy disk. Okay, so this various evolutionary mechanism can act on a galaxy, but the galaxy retains its disk. That'll become important later. Now, this is a talk on galaxy evolution, so I'm contractually obliged to show you a Hubble tuning fork diagram. But really, it's a nice way of thinking about our understanding of classifying galaxies. And so up until recently, the most common way to classify galaxies was by their visual appearance. So Hubble back in the 1920s, looked out into the night sky and he made his tuning fork, right? So in the handle of the fork, we have these elliptical galaxies, these red blobs. In the prongs of the fork or the tines of the fork, we have spiral galaxies, barred or unbarred. And in the middle, he put the lenticulars because he didn't really know what was going on there. He thought they might be an intermediate product. Now, back in the day, Hubble thought that galaxy evolution occurred from left to right, so that these big blobby things gradually evolved structure. Although recently we started thinking that it was happening in the opposite direction. Things like spiral galaxies are undergoing many, many mergers over their lifetime and ending up as big spheroidal blobby things. But I want to highlight that it's not really an evolutionary sequence. So a galaxy can start off as a spiral and end up as a spiral. It can stay a spiral its whole life. It just depends what mechanisms acted on it. But just to say that galaxies will not all end up in this elliptical handle here, okay? So another issue that I have with classifying galaxies by their visual morphology is that it can be a little bit deceptive. Now, what do I mean by that? Quite often, this light, the light profile of a galaxy is hiding the complex processes occurring, under the hood, I suppose you could say. So for example, there's 3 galaxies up here, 2 of these galaxies actually contain a significant disk component. So a disk of stars rotating in a plane, right? The other one is a true, what we'd call spheroid galaxy or elliptical galaxy. The stars are all on random orbits. My challenge to you is to figure out which one is the true spheroid, because to me, they all look fairly identical. Now, normally at this point, when I'm giving this seminar in a lecture theatre, I can see the audience and I ask you all to raise your hands. I don't know if we're going to be able to do this today, so I will ask you now, in your own mind, to make a choice. Which of these galaxies, just by looking at them, which of these galaxies you think is the true spheroid? And hopefully I've given you enough time. It's Galaxy 1, Galaxy 2, or Galaxy 3. Now, to show you your response, congratulations if you thought it was galaxy number 3. You'll be right. Now, I'll explain what these plots are down the bottom in a moment, but you can already see that the 2 galaxies on the left, these maps here look quite similar, right? You have these big blocks of blue, white, and red, right? Whereas this one over on the right looks very higgledy-piggledy, a bit of a dog's breakfast. Everything looks a little bit random, right? So this one here, that's our true spheroidal galaxy. But I do hope that what you take from this is that it is difficult to separate these different types of galaxies, right? Just based by looking at them. So that's why we need to go a little bit further. Now, a quick aside before we do go further, which is to talk very quickly about integral field spectroscopy. Why have one spectrum when you can have many? So imagine you have this galaxy here, right? And you're interested in, what's going on in the galaxy. So traditionally what you'd do is you'd pop down your fiber and you'd take a single spectrum of that galaxy. And generally you take it of the central region because it's the brightest, right? Now there's a whole wealth of information that you can get from a galaxy spectrum. Possibilities are almost endless. Very useful stuff. However, you'll notice that this galaxy looks very different on the outskirts to what it does in the center, right? It's a very different color, probably indicative of very different physical processes occurring. So in that case, what we derive from this central spectrum might not be indicative of what's happening on the outskirts. So instead, what we do is we put a whole bunch of fibers down across the face of the galaxy, and we take a whole bunch of spectra. That's the concept behind integral field spectroscopy. So for example, what you could do is you could take this line I've highlighted in yellow here. This is the hydrogen alpha line. It's a very good indicator of current star formation, among other things. You could measure the size of this line, or the flux of this line, across the face of the galaxy, and you would get a map that looks like this. So this is showing you, in white, these little blobs are the areas where we're seeing the most active star formation in this galaxy. And you'll realize that the size of these blobs is about 1 kiloparsec. So the resolution of these maps, this come from the Manga survey, is about 1 kiloparsec. Right? The other thing that you can do is you can measure very tiny microscopic shifts of this hydrogen alpha line with respect across the face of the galaxy. And then you can measure the motion of the gas, the ionized gas within this galaxy. And you get a map that looks like this, which probably looks similar to the one in the previous slide with the red, the white, and the blue, right? You can imagine a rotating disk of gas with the sort of red region of this, this map receding away from you, the blue region coming towards you. And in that sense, you have a rotating disk. This is for stars, for ionized gas, but you can do the same for stars. Okay. So with all that said, and thinking about the way we can make these maps of velocity or flux and things like this, I present an alternative way to classify galaxies, and that's based on their stellar kinematics, so the motions of their stars. And so here I show you not the Hubble tuning fork, now we've upgraded to a comb. This is the tuning comb, presented in several works based on the motions of the stars, the stellar kinematics. Now you can still put a dividing line down here, and everything on the left we call slow rotators, okay? So these are the galaxies that have these velocity maps that look like a bit of a dog's breakfast. And I've put a couple of example stellar orbits on just to give you the idea that the orbits are random. The galaxy is still gravitationally bound, but it is what we call this true spheroid. Okay, they tend to be fairly red, and we call them also dispersion dominated. the metric that we use to measure them is this lambda-r parameter. And really all that is just the degree of rotational support to dispersion support within a galaxy. Now over on the right-hand side of the diagram, you've got what we call the fast rotators, and they look a bit like this. You'll see this characteristic red, white, and blue, very nicely ordered rotation map. And so these indicative orbits that I put on here, you can see they're all nicely aligned, right, into what we call a dynamically cold disk of stars. And so we call these galaxies rotationally dominated. And if you're measuring the degree of rotation to dispersion support, this lambda-r parameter, it's about 1. So you say, great, you've come up with a new classification scheme. What do galaxies look like in this parameter space? Well, something like this. So this is our lambda-r parameter on the y-axis that I've just described, rotation to dispersion support. And we're just measuring that as a function of the ellipticity of the galaxy. Now, this plot by Becky Smethurst is really nice because for every galaxy data point, she's actually plotted the velocity map of the stars. And you can actually see down in this bottom region here, in this sort of weirdly shaped box, you'll see the slow rotating region where these dispersion supported galaxies are. And you can see there's not a lot of structure in their velocity maps. Whereas in the fast rotator region, which is sort of the rest of the parameter space, you see there is a lot of really nice structure. And so this is where these fast rotating galaxies lie. So that's fantastic. This is a nice new way to be ordering galaxy kinematics. But you might ask, well, in that case, is there a link between visual morphology and kinematic morphology? Are all spiral galaxies fast rotators? Are all elliptical galaxies slow rotators? The answer is not really. So this is the exact same parameter space I just showed you. This lambda-r parameter as a function of ellipticity, the same sample of galaxies, the Manga Galaxy Survey. And this time the galaxies are sort of shown, or the contours shown are various different morphological types. Now you can see while in the slow rotator region of this diagram, there seems to be only elliptical galaxies. The elliptical galaxies really extend quite a ways up this lambda-r axis. And you can see there's almost 100% crossover between S-zeros and spirals, which I agree the color scheme is not great here. So it's all a little bit of a mess. There's no one-to-one link between the two. So that's why I think it's very important to be studying the stellar kinematics of a galaxy, because that's telling you about the actual structure of the galaxy itself. And then we can go ahead and link that to other interesting features such as the star formation history of the galaxy. So that's what we're going to do now. Before that, though, one final question for the audience to keep you all awake. Kinematically, okay, so using that the description that I just presented, what fraction of galaxies in the local universe do you think are disks? And I've added a couple of caveats. It's a relatively massive sample. This fraction is by number, and this is a volume-weighted sample. So your three options are here. Have a think. I'm not going to call on anybody, and I'm not going to ask for a raise of hands. I think I've given you enough time to think, though. The answer in this case is actually 95%. 95% of local universe galaxies are disky galaxies. Now, you might think that this number is very high, but let me convince you. So this is how I went around it. I took the Manga Galaxy Survey again, and I measured not the lambda-r parameter, but a very similar one called V on sigma. Again, the degree of rotation to dispersion support within a galaxy. And for a given mass bin, I did a histogram of this V on sigma value, which you'll see here. I did separate out the fast rotators from the slow rotators because they are two separate populations. And what you'll see is a bit of a Gaussian with a tail. And then I fit a really bad fit here, right? This is a terrible fit. A single Gaussian to something that obviously has a clear tail. I'm aware. What I did was I started with the assumption that this log V on sigma distribution for dynamically cold systems, so disky systems, would be well approximated by a normal distribution, which will be matching the distribution of spin parameters of dark matter halos in galaxy formation simulations. So fine, I did this, took 1 sigma from the peak, and I put a little gray line down. Sorry, just 1 second. Pardon me, I was sick last week. You see this grey line here, 1 sigma away from the mean. Everything to the right of this, I have called a dynamically cold disk. So these galaxies are rotationally supported. What about this population to the left? These things are still rotationally supported disks. They're still classified as fast rotators, but they're not rotating as fast as the cold disks. So for want of a better term, I call them intermediate systems. Now, assuming that you're happy with the way that I've done this classification, which I agree is quite qualitative, but it's interesting to see the trends that come out of it, you can go ahead and do the same. So you can define these 3 kinematic classes, slow rotators in red, the cold disks, and the intermediate systems. And you can do the same thing for 3 other mass bins, getting more and more massive. You'll notice in the highest mass bin that the slow rotators become important or more frequent. That's exactly as we expect, given that we think that their origin is from repeated mergers. So if you have repeated mergers, you've probably built up a lot of mass. So fantastic, we can take this information and have a look at the number depth counts of these galaxies in the local universe. But before we do, of course, again, this is a galaxy evolution talk, and I haven't shown you a picture of a galaxy for a little while, so here are 3. I still think that it's very difficult to classify the dynamical state of the stars in these galaxies just by looking at them. Maybe you're better at this than me, but just to say they all look fairly blobby. So what is the most common galaxy type? So coming back to this, this is a mass function. So let's start with looking at the black line, which is all galaxies in the Manga sample, volume weighted. So what we're plotting here is just the number of galaxies in each stellar mass bin. And you can see reassuringly, it looks a lot like a Schechter function, as we should hope. And then the 3 colored lines here are the 3 kinematic classes that I just defined. So in blue are these pure disk galaxies. And you can see, because that blue line is so close to the black line, these galaxies are dominating at basically all stellar masses. Things get a bit murky at the very high mass end, but for most stellar masses, pure disks are the most dominant. In fact, 60% of all galaxies are these pure disk galaxies. These intermediate systems are still numerous in this total sample, and so totaling 95% of the whole sample. This is a log scale, so you can see these slow rotators really do fade into the background for most stellar masses until we get to the absolute highest stellar mass bins where there aren't many galaxies to begin with, but slow rotators are the most common in the highest mass bin, at least. But these slow rotators account for only 5% of all galaxies, or 10% by mass, and this is very different to what had been found in photometric studies, so visual morphologies of galaxy evolution making these same plots. So this is nice, but this is not new. What is new and fun is to split this mass function by star formation rate. So we take now just the galaxies that we deem to be star forming, and we make this same plot. Now you'll see here the blue line is almost right on top of that black line. Okay, so basically all star forming galaxies are these pure dynamically cold disks. Now, why is that the case? This is where I get a little bit speculative, but I have some more fun with Keynote. So imagine you have a galaxy disk, okay? Your galaxy is undergoing star formation, which is great. Star formation generally induces outflows, okay? Or feedback, some people call it. So it ejects gas into the halo of your galaxy. It condenses within the circumgalactic medium, the CGM, which is generally formed of gas which has higher angular momentum. It condenses and it rains back down onto the galactic disk. So you're raining back down gas with higher angular momentum. And thus you're increasing the angular momentum of your disk. So you have this continued accretion of angular momentum. Now this is a little bit of a catch-22, because to gain this extra angular momentum, you need to be star forming, because you need these feedback-driven outflows. If you stop star forming, you stop your outflows and you stop gaining this extra angular momentum. Okay, so these galaxies here have probably been star forming for a long time. Now, what about if we look at the passive sample? So these are the passive galaxies here, and you can see. So the dominant population here are these intermediate systems shown here in green. So these are galaxies, like I said, still disks, but not as disky. So is that because there's two reasons here. Either they have grown structures which are more dispersion supported, that brings down your V on sigma value, or they didn't have the opportunity to gain as much angular momentum as their pure disk friends. So maybe they quenched their star formation early. It's hard to say just by looking at these plots. The other thing that I will point out, though, about the passive sample is that there are still some passive pure disks. In fact, it's 30% of the population. What this is telling me is that there must be multiple quenching pathways, okay? You can quench by lowering your V on sigma, or you can retain your V on sigma or decrease it and still be passive. So galaxy evolution is complicated. We knew this already, right? So what is causing this intermediate population, and is it bulges? That's what I want to continue my talk about, bulges. So what is a bulge? Well, if you ask Wikipedia, it's a terrible definition, a tightly packed group of stars. Just me, it's kind of useless. The definition I'm going to use is a structure that bulges out of the disk of a galaxy. So if you look at a galaxy edge-on, anything that you see bulging out of the disk, we call that structure a bulge, okay? That said, recently on the GECKOS Slack, I asked what I thought was quite a simple question on a Friday afternoon. I said, hey, everyone, what do you think, like, how would you define a bulge or a classical bulge? I gave a couple of options. Then I went home for the weekend. I came back to this. An absolute cavalcade of discussion. Almost enough to write a paper, although unfortunately we did not come to any sort of agreement. Everybody had different opinions, so the jury's still out. That said, there are generally 3 different types of bulge. Excuse me. You might have heard of classical bulges, such as this one shown here. These ones, if you fit a light profile to your galaxy, you'll end up with a Cercic index of 2 or greater. And we see these structures as being old, pressure supported. You might say they're like a mini elliptical. If you look at the orbits of the stars and galaxies like this, you have your disk still, in many cases, stars that are rotating nicely, but then you have this central region, which the bulge region where the stars are all on random orbits, and yet pressure supported. So we think classical bulges form through merger processes, among other things. Then we have these things that people call pseudo-bulges, or disky bulges is probably a safer term. The orbits of a galaxy like, the stars in a galaxy like this would look something like this. So you have your main disk of stars. This galaxy has a bar, so you have bar orbits. And then the bulge itself is still a disky structure. So the stars are all still on disk orbits. We think these bulges are built via what we call secular processes. So for example, gas inflow from a bar, okay? Now the final type of bulge that I want to talk about is boxy peanut bulges. For this, though, you need to turn your galaxy on its side. And you see this X shape. I'm hoping you can see that in this image. So like this. It's called boxy peanut, well, because allegedly it looked a bit like a peanut at some point. So this is the outer plane projection of a stellar bar. So you have your galaxy disk, a bar forms. After a gigayear or so, this bar buckles out of the plane of the disk and forms this X shape. The stellar orbits are a bit hard to show, but you still have a disk of stars, and then in a projection, you'd see sort of this infinity symbol of the orbits in the boxy peanut bulge. Okay. So those are the 3 main types of bulge. So when we come back to the question of what's quenching star formation in galaxies and is it bulges, more than 10 years ago now, in 2011, the story seemed quite clear-cut. It was nice. If you plot, this is my favorite parameter space here, the star-forming main sequence. So this is just star formation rate of the galaxy as a function of galaxy stellar mass. And you'll see this nice line along here, this nice structure here. This is the star-forming main sequence. So all this means is that the more massive your galaxy is, the more stars it's forming, most of the time, okay? You have these 2 regions of this plot. So above that white line, the star-forming main sequence line, we call these galaxies starburst. So they're forming more stars. And below is the passive region. So these galaxies are forming not as many stars for their stellar mass. However, you can see from the color coding of this plot, which is Cercic index, that the galaxies on the star-forming main sequence tend to be very disky, okay? Whereas these things in the passive region tend to have very high Cercic indices, indicative of classical bulges, like I was saying earlier. So the idea being that the galaxy grows a bulge and the bulge quenches star formation. This idea is sometimes called morphological quenching. So that all seemed tied up in a neat little bow in 2011. Then in 2021, so 10 years later, we came along and we made the same plot, star formation rate as a function of stellar mass. But this time, the bins were color-coded by this lambda RE parameter, remembering that a high value, the galaxy is very rotation supported, low value, the galaxy is very dispersion supported. Now, following this main sequence line, you can see that all galaxies on the main sequence are very disky. Okay, so very rotation supported. That's in line with the Roots paper. However, if you move below the star-forming main sequence, you can see only in the highest masses do you see these low values of lambda. So these truly dispersion-supported systems, or maybe prominent classical bulges. For most of these passive galaxies, the lambda value is lower than the galaxies on the star-forming main sequence, but not so low as to pop them in the slow rotating regime. So the question is, have they grown extra dispersion-supported structure, or is there another reason why these galaxies are passive? So I said, is it classical bulges? Not necessarily. It depends. And so I think this brings us into a bit of a tension between photometric and spectroscopic results, in that if you look at the fraction of different bulge types as a function of stellar mass from photometric surveys, at high stellar masses, you see basically all bulges are classical bulges. However, I present you with a different possibility. Take this galaxy here. Okay, this galaxy has a bar and a strong bulge and a ring. If you take its surface brightness profile, so you're just measuring the galaxy flux as a function of radius, you get that black line. Now you can fit that line quite well if you do a 2D a light decomposition with an n equals 4 Cercic bulge and an exponential disk. Okay, so you'd say, oh, that galaxy has a classical bulge and a disk. We fit the light profile, we can go home. However, if you're actually a bit more careful and you fit that same light profile with a whole bunch of different structures, which are all disk-based, you can actually fit that underlying light profile better. So in this case, we included a ring, an inner disk, a bar, and an outer disk. And so is it possible maybe that instead of classical bulges that we're assuming, what we're actually seeing is this superposition of multiple disky components contributing to our light distribution? Is it disks all the way down? So it's very difficult to do these very detailed photometric decompositions. You need very nice data, very well-resolved data. So it's tough. You can't do it for, say, Sloan. So instead, why don't we check the stellar kinematics, right? And we tried. So we tried with Sami and Manga. We tried doing these bulge disk decompositions from IFS data. And we got some places, right? I wouldn't say that there was a definitive answer because there was a lot of issues with these works. And I'm on many of them, so I can say that. The issue is you still need to make assumptions. You still need to assume that a galaxy has a bulge and a disk, which we don't know that's necessarily true. You also have contamination of disk light in your bulge and vice versa. And really the main issue, though, is that the central structures are just not resolved enough. So remember I said earlier that the resolution of Manga is about 1 kiloparsec. Your average bulge is maybe 1/10 of that in size. So you're really not resolving these central regions. I think that's really the main problem. So I hope that I have sufficiently motivated the GECKOS survey now, which I'll introduce to you quite briefly. So the GECKOS survey, which has a very long and contrived acronym, which was my fault. What we are is we're doing very deep observations of 35 disk galaxies, all of Milky Way mass, and all edge-on. Why edge-on? Well, multiple reasons, but the reason that I'm interested in is that we can see the light bulging out of the disk, right? So we can actually measure and separate this bulge light from the disk light because the galaxy's edge-on. We have a lot of aims of GECKOS. So we're a MUSE large program, as was said, 317 hours currently being observed. And our aim is to understand disk galaxy evolution, linking that back to what we know about the Milky Way. Okay, so all of these galaxies, and this family portrait I've got here, is arranged from most star forming all the way down to least star forming. We span 2 decks in star formation rate at Milky Way mass. So the idea is that all of these galaxies have assembled a Milky Way's amount of mass, but given their current star formation rate, they've clearly all gone about it in very different ways. We want to understand that diversity of assembly histories. That's the main aim of GECKOS. We can also do some fun things by testing the predictive power of galactic chemodynamical models. We apply the galactic models to external galaxies. Where do they break? So that's what we're working on too. We're actually a multi-wavelength survey these days. So we started off with MUSE, but we've also got some decent amount of ALMA time, some MeerKAT time, and a little bit of JWST, hopefully more to come. So we're looking at this multi-phase problem as well. Now, the best thing about GECKOS is that we have extraordinarily good spatial resolution. These galaxies are all really nearby, distances of less than 70 megaparsec. And so our spatial resolution is on orders tens of parsec. Not quite as good as the FANG survey, if you've heard of this one, but still to the point where we're going pretty well. And so we're hoping to be able to resolve the physics of galaxy evolution at the scales that we haven't been able to do previously. I should just briefly shout out the team. The PI there is Yasser van der Sunday. The steering committee includes myself, Marie Martig, Deanne Fisher, Michael Hayden, and then we're a team of about 70 now. We are an open collaboration, so if you have project ideas, please contact me or the science coordinator, Marie. We'd be happy to discuss membership with you. Now, before I show you any fun, exciting first results from GECKOS, however, I will just very quickly plug the NGIST pipeline too. So this is developed to analyze our GECKOS data, but it's actually applicable to all Galaxy IFS data. So it's your one-stop shop for Galaxy IFS analysis. The idea is that we take your input Galaxy data cube, you perform some boring steps, binning, spectra preparation, these sorts of things. Boring but important, I should say. And then you can perform any number of science modules. Now, this NGIST pipeline started from the basis of the GIST pipeline, which you might have heard of, that was developed here at ESA a few years ago. But we've made a lot of improvements, especially related to memory file handling, to bring it up to date to be ready for sort of modern data sets. If you're mosaicing, 3x3 MUSE pointings, you've got, a 40 gigabyte data cube, your memory starts to become an issue. So we've been dealing with that and also making some science improvements too. So the science modules that we have include one that determines stellar kinematics, so the motions of the stars, gas, ionized gas, fluxes and kinematics. And then we have 2 stellar populations modules, one that uses full spectral fitting, so PPXF, and another that uses good old-fashioned Lick indices, because you should always compare to Lick indices when you're doing stellar populations. So NGIST is great for many reasons. It's modular, so if you only want to use one of these modules, you can, so it'll save you time. It's like I was saying, we've made quite a lot of memory efficiency changes. We've documented it as well, which is nice. It's still being actively developed, so if you have any science case for which NGIST does nearly everything you need it to do, but just one extra thing and to make your life so much easier, you get in contact with me, the lead developer, and I'd be happy to consider incorporating that for you, or else you can help develop as well. It's suitable for any Galaxy IFS dataset, like I said. We developed it for MUSE, but it is applicable to others. We're testing it on Weave at the moment as well. Modifiable, and we have this handy quick look interface, also part of GIST, which is called Map Viewer. So you can have a very quick look at the output. Say this is a velocity map of your galaxy. You can see the PPXF fit, see whether it was good or bad. And it just shows you a couple of stellar population parameters and a very rough and ready star formation history too. But it's incredibly useful, I find. So that is all free, available for download on GitHub. And please, we would like as many people to use it as possible. But time for some very quick GECKOS results. So I'm going to show you 2 galaxies in detail. Top one is a very boring galaxy. It's just a disk. The bottom one, I hope you can see the boxy peanut bulge, that X shape, right? This is my favorite galaxy here. This is imaging, Decal's imaging. Okay, so very deep imaging. I'm going to overlay the MUSE cubes. Okay, so these are reconstructed 3-color images from the MUSE cubes. And you can see, if you compare especially these regions where you've got these faint background sources between the imaging and the MUSE cube itself, the MUSE cube is actually deeper than the imaging. Okay, and that's because we're sitting on these sources for up to 12 hours at a time to reach our surface brightness constraints. We wanted to go extraordinarily deep because we have a lot of science related to stellar populations of the thick disk, which is very faint. So these are very beautiful. And remember, of course, that every single one of these pixels is a spaxel and has its own associated spectrum. So for me, that's quite mind-boggling. I think they're really beautiful. So some results from NGEST. Here are some rotational velocity, stellar velocity maps. You can see this top galaxy up here is really boring. There's nothing exciting happening whatsoever. Now, this bottom galaxy, you'll see this little 2 blobs here, little snakebite pattern, which look a bit separate from the rest of that outer disk, right? We think this is a nuclear disk formed by the bar, which is really cool and really nicely resolved too. I'll show you a few other maps. This is the stellar velocity dispersion map, and you can see dispersion is very low in this plain pure disk galaxy. Yeah, not much is heat in those stars. Whereas the bottom one is quite interesting. You'll see this higher velocity dispersion region in the center, but it's a bit of a weird shape. In fact, we call it the croissant. So it looks a bit like a croissant, I think. But then you have this central region of low dispersion. Again, we think related to a dynamically cold nuclear disk. You can look at also the high order velocity moments if you're interested in that. There's not a lot of structure in the top map, but in the bottom one, you can see the nuclear disk sticks out like a sore thumb. It's super clear. We also see some structures related to the presence of a bar. So the non-axisymmetric nature of bar stellar orbits show up quite nicely in these high order maps. And so this is something that I've been working on. Moving to the ionized gas, this is H-alpha flux. So remembering what I said earlier, that H-alpha is an indicator of current star formation, among other things. These are binned maps. These are binned because we wanted to do stellar kinematics and populations. We don't need to bin these. We can do these on spaxel scale too, and they look even more fantastic. But just to point out that you can see these individual H2 regions in the GECKOS galaxies too. So FANGS hasn't cornered the market on individual H2 region science just yet. And we can also do things like velocity maps of the ionized gas as well. Here we see some really characteristic streaming motions, as you would expect if you have a bar in your galaxy streaming the gas towards a center and onto a nuclear disk. Finally, I'll show you some stellar populations, although I'll say this is work in progress and something that we're actively working on as a team to improve this as much as possible. This is the light-weighted average stellar age of these galaxies. So the central region, or the thin disk region, is quite young, as expected for a galaxy, and the outskirts are a bit older. And you see similar in PGC as well. And then the last one I'll show you is stellar metallicity. You'll see a metal-rich central region and more metal-poor outskirts in this galaxy. And you can see the nuclear disk in PGC 44931 is really, really metal-rich, as you might expect if you have a whole bunch of star formation, a whole bunch of generations of new stars happening very quickly. Quite enhanced. And also, maybe to guide your eye, I don't know if you can see or not, this sort of X shape that you can see in the metallicity map at PGC 44931. Maybe I've been staring at it too long, but I think this is the result of this boxy peanut structure. So you had a thin disk of metal-rich stars, you buckled your bar, and you shot these high metallicity stars up onto these orbits out of the plane of the disk, which I think is really cool to be seeing. So coming back to, we have a full sample of 12 galaxies at the moment, which is our first data release internal for the time being. And just to show you an example, I'm not going to show you all of the different maps, but these are the velocities, stellar velocity maps of these galaxies. You see a lot of actual structure. Dust planes become apparent, which is annoying, but these two galaxies here have this nuclear disk structure. So I showed you this galaxy earlier, but there's another one down here which also has this nuclear disk structure. Finally, I was interested in diagnosing bar structure in these galaxies, which is quite interesting. You can take it from the dispersion maps, but also the high order maps in comparison to the velocity. We found a couple of galaxies that had, first of all, these two croissant features, here and here, but also we saw peaks in velocity dispersion, and we thought, there's your classical bulge. Classical bulges should have high velocity dispersion, 130 kilometers per second. However, it turns out you can actually just explain these high velocity dispersions if you also have a stellar bar that's relatively close to being end on. Now, this galaxy, if you take also its high order velocity moments in combination with the velocity and the sigma, definitely has evidence of a bar. It also has a box peanut bulge in the photometry. So we're actually relatively certain that in this case and a couple of the other cases, this one here too, these really high spherical looking bulge structures are actually end-on bars, masquerading as classical bulges. So to answer the question that I was interested in, which is what's at the heart of GECKOS galaxies, we sort of came up with a bit of a classification system. Most of them, it turns out, were barred in our first sample of 12, which was unexpected. We had one weird one, which was a counter-rotating disk. We're writing a paper on that. But apart from that, and our bulges wonder down here in GC3279, what we didn't find were any classical bulges. Now, this is a work in progress. This is 12 galaxies. We have the rest of the sample to come, but it is looking as if it's possible classical bulges are less common than we might have previously thought. What's the implication for galaxy evolution? Well, maybe mergers aren't quite as important as we previously thought. Maybe we don't need to invoke as many mergers to make the structures that we see at redshift 0. The one final thing that I'll leave you with before I get to my conclusion slide is that we can quantify this as well. So all the maps that I showed you were beautiful, but quite qualitative. Some work that my student, Tom Rutherford, is doing at the moment is he's taking these same galaxies and he's performing Jeans anisotropic modeling, JAM modeling, which is a form of dynamical modeling. And he's asking what happens if you take the light profile of the galaxy, you fit an MGE, and you fit a single axisymmetric disk to our data. So this is our data. He creates a model of just one plane rotating disk, and then he subtracts the model from the data to look at the residuals to see what is left over and what that tells us about any possible non-axisymmetric structure within the galaxy. So straight away, you can see there's actually quite a lot of structure in here. First of all, that central region, that's a nuclear disk again. This region here we think is due to the bar. So these non-axisymmetric orbits from a bar. This outer region we're still looking into, but it's possible this galaxy has two-disk structure, a thick and a thin disk, and that they're dynamically distinct enough that just fitting one disk will not do. So stay tuned for work from Tom in the future. And then just before I finish off, I forgot that I was also going to talk about the future. So kiloparsec scales, we did a lot of fantastic science and still are. Tens of parsec scales, we have these new surveys. FAMS has been around for a while, but things like GECKOS and MOVE that I'm both involved with on MUSE, you know, just starting to marginally resolve like these tiny structures in galaxies that are actually going to give us the physics related to the galaxy evolution, with the idea being that in the 2030s, we have all these new exciting ESO facilities and instruments coming online. So two that I'm mostly excited by is the ELT, which I'm sure you've heard of, Harmony, which is the IFS going on the ELT, and also the MAVIS instrument, which is going to be a diffraction-limited integral field spectrograph mounted on the VLT in about 2030. So some fancy work with lasers and AO mean that we don't need space telescopes anymore. No, we do need space telescopes, but we will have diffraction-limited resolution on an 8-meter class telescope, which is going to be super exciting. So with all that, I'm going to leave you with my conclusions. If you take anything from this talk, the universe is disky. There's disks all the way down. What's quenching galaxies? Is it the structures within them? Is it bulges? Well, there's evidence for and against. I'm not willing to say at the moment. However, in this GECKOS sample, when we're actually able to highly resolve these central regions, we're yet to see any evidence of a true classical bulge. But stay tuned. So I will leave it there. Thank you all so much for listening.
Thank you very much, Amelia. Great talk. Very interesting. So we have time for question. You can unmute your microphone if you want and ask a
Okay,
question.
I
Patricia.
Hi, Amelia. Nice to meet you. Nice to see you again.
Hi, Patricia.
Been very nice talk, by the way, very didactic. I wonder about when you saw the stellar metallicity in the edge of this for the gecko sample. I'm going to put my camera.
See if I can get back there for you. Yep.
Yeah, the scale is that set that is like the maximum metallicity you are getting is minus 0.2.
Yeah, that's about right, or maybe minus
Maybe
0.3.
yes,
So
reach a
quite,
little bit higher. Okay.
yeah, quite metal poor. Quite
Mhm.
metal poor for these two
Interesting.
galaxies. Yeah, yeah.
No, that's interesting. And if you go to the previous, the stellar kinematics, you commented, I think it's this galaxy, which is, you see 00903. But can you put the map again? Because it was amazing. It was like, it's
The
not like
stellar
a,
kinematics?
yeah.
Yeah, look, I'll just show you them all. There you
Yeah,
go.
exactly,
Yeah.
that one, no? On the
This is
right,
the one that we were
upper
looking
right.
at, yeah.
The one, no, I'm talking
Oh,
about
this
the
one
one
here.
on top. Yeah, that one.
Ah, yes, a delightful weirdo. Yep.
What's going on there?
Well, we think it's a counter-rotating disk galaxy. So you have this one disk of stars rotating in this direction, and then you have a second disk of stars rotating in that direction. I can only assume merger origin. But this is something that our PI, Yasavanda Sunday, is looking into at the moment. He's performing, well, he's using Marie-Martigue's Bayes LOSVD code to really look at the LOSVD at different regions to try and understand, well, to try and get some idea as to how this thing might have formed. I can say that the ionized gas only follows the inner disk. So the outer disk of stars, but there's no gas there.
Okay.
Yeah, it's an interesting one though. Yeah.
Amazing. Very nice. One more. You mentioned at the beginning of the talk that, well, did you you fit to separate the galaxies into high rotating, mid rotating, and non-rotating, no? And you that's probably not directly related with what you show, but you say that you will expect that the spin distribution will follow the ones of the dark matter halo. And my question is, has someone looked into that in numerical simulation? Is that really true? Because I wonder is that true or not?
Oh, that's a good question, and I'm not the person to ask because I'm very steadfastly an observer and not a simulator. This is what I was led to believe by my conversations with simulator friends. So I might have to divert that question to somebody who knows more about cosmosims. Yeah.
Well, thank you. I will just a comment, just the last one. When you saw the stellar kinematics, that you saw that in the center there were like two regions, no, of lower stellar velocity dispersion, no,
Oh yeah, the
in
dispersion
one of the
maps.
galaxies.
Yep.
Just have a look at one paper of Adriana de Lorenzo Cáceres. Because he also, he's found that in several galaxies. He thinks it's due to the inner bar and the composition of several components while they do numerical simulations to so that can explain those drops at the end.
That's a really good point, and that's something that I haven't considered, that there would be inner bars in these galaxies, because I think we just don't have the spatial resolution to resolve. I think I'm fairly confident in saying that there's a nuclear disk there of order that size, but anything within that, any inner bars, I think we're going to need some better observations. Or it would be lovely though. That would be a fantastic thing to be able to see. But I don't think we're going to get it quite out of the GECKOS sample, unfortunately. They're just too small.
Okay, I think okay. I was talking about another one. I think maybe a different sample that you saw like two little hollows, or it was that one? I don't know.
So there's this one. I hope you can see my mouse. This one here.
Okay.
Yeah. So the sigma drop, or whatever they like, it's been called sigma drop in the literature. And this one
that
here.
Could be that could be. Yeah, I would guess that that's an internal nuclear disk as well. Yeah, that's one. But I don't know. I have in my mind that you have like two blobs but maybe I don't know why. Maybe I look into it and I saw something different. But no, I will guess that a nuclear disk as well. Yeah. I think so. Okay.
Yeah, thank you.
Thank you. Thank you to you.
We have another question from Tanto.
Yes, maybe I will put the camera. Hello, I'm Teresa Antosa. I'm not from the Complutense, I'm from the University of Barcelona, but I connected. It was a very interesting talk. Thank you very much. So also for these two cases that you've showed with more detail, I'm from the Milky Way world, so sorry if I ask a naive question, but in the first one, the NGC, in the metallicity plot that you can see in the outer parts of the disk, that the metallicity is very low at high Zs, or is, I mean, in the outer parts only, is this, well, but it's very high in the outer parts of the disk. Like you don't see like a vertical gradient, but actually you see higher metallicities at the borders of the disk. Is this expected or?
So just so I'm clear what you're talking about, are you talking about this higher region here?
Yes. Yes.
Yeah.
Or the problem of the borders or?
So, and actually we would love to talk to some Milky Way people about this. My understanding is that the Milky Way's thin disk flares a little bit. And so one possibility would be a flaring. However, and actually I should say this galaxy has been decomposed by, I think, Sebastian Comoron to have a thick and a thin disk as well. However, I'll give you a bit of inside baseball. This galaxy is made up of two MUSE pointings, 1, 2, and the dividing line is about, if you can see my cursor there. Now, what you'll also notice is that that's kind of where these outer regions go from very dark purple to a lot lighter in color. So there is also a possibility that we're investigating that this is an issue with our flux calibration or our sky. And unfortunately, stellar population analysis is really sensitive to the shape of your spectrum. And if your flux calibration is even slightly out, that throws off the shape and wreaks havoc.
Okay.
So we're looking into both possibilities, and I say that just to be incredibly transparent. We're not the only survey that has this problem.
No,
I
I
think
mean, it's something
Kang's also. It's an issue that modern IFS surveys have. But interestingly, we're only seeing it for some galaxies, not all galaxies. So you'll see this galaxy here behaves quite nicely. So we're not sure if it's physical or not, and we're looking into it. If it's physical, that would be super cool. But I'm also being very careful. We're not publishing anything that anytime soon. But thank you for a comment. That's very insightful.
Thanks to you.
Any other questions? Well, I have one. I was wondering when you show the kinematic maps of the ionized gas of the, we can say, more interesting galaxy, PGC. I was wondering if you also expect to find the same sigma velocity dispersion map for the ionized gas, similar to the stellar component, if you see the same features.
So that's a really interesting question. And I think the answer is not necessarily. There's some stellar structures that exist that won't contain gas. So for example, the boxy peanut structure that I was talking about shouldn't contain any gas. That should just be stars only. So that's not contributing to any increase in dispersion, measured dispersion. So I would imagine that and I can't remember because I didn't include it in this talk. I would imagine that the ionized gas velocity dispersions are a bit more well-behaved, say, than what we're seeing in the stellar velocity maps, just because the gas is a bit, I hesitate to say more boring, but behaves much nicer than just the stars.
Because in this galaxy, we have a bar, right?
Yes, there is a bar in this galaxy, yeah. So that's what you can see here. These are sort of indicative of some sort of streaming motion of the gas going along the bar and depositing itself into this nuclear disk region. And
I was wondering if maybe we are too phase on age-on, to properly see, for example, any gradient in the metallicity within the bar. So I think it could be complicated with this kind of sources.
I think that there's other samples better suited to that than ours, because the other thing I haven't mentioned much of is dust, right? These are all mostly star-forming galaxies, so you have dust when you put a galaxy edge on. While there's definitely some benefits, and that's the science we're trying to do, the drawback is that dust blocks a lot of the light in the midplane. Not much we can do about that, sadly.
No. Thank you. And lastly, curiosity, you mentioned the NGIST pipeline, and I've never used it, but I'm interested in it. And I was wondering if it's possible to apply multi-component Gaussian fit.
So in theory, absolutely, because but in practice, you would have to write your own module to do that. So if you're doing, for example, stellar kinematics, you could copy the stellar kinematics module, add in a couple of edits so that you could do, if you're using PPXF, you could just include a multi-component fit, which is very easy to do in PPXF. And then you could run that module instead of the stellar kinematics module. So that's stuff that we're happy to work with you or with the community in implementing, because, well, I think a lot of the hard work is already done in terms of these preparatory steps. And so slotting in something like a multi-component fitter is definitely possible. We just, people power limited, unfortunately. I have a list a mile long of updates I'd love to make and things I'd like to implement, but we're hoping it'll become more of a community effort with multiple people.
Also for the emission line, for the gas emission, right?
Same,
it could be...
They're both PPXF based.
Because I guess that you don't have any outflow emission here in this sample.
We have a lot of outflows because a third of our galaxies are very star-forming.
Okay.
This is a big problem. This is something that our multi-wavelength coordinator, Deanne Fisher, is working on. She has her own bespoke software to do multi-component emission line fitting called Thread Count. So if you're looking just to do that, I would recommend using her software as well, which is also publicly available. But yes, there will be a lot of outflow science coming from GECKOS in the coming months.
To do.
Absolutely.
So if there are no more questions, I think we can stop here. Let's thank Amelia again. Sorry. Thank you very much.
Thank you.
Amelia.
Thank you.
And thank you very much
for the tool for analyzing the data use. We'll try it.
Thanks, let me know.
See you, everyone. Thank you for joining us.
Thank you.
Thank you, Amelia. Bye. Bye. Thank you.